Yeah, good morning, students. It's my pleasure to introduce this another important application of this stack data structure in this particular CDT. So now I would like to share my screen. Yeah, hope my screen is visible to you. Yeah, in the previous class, we had a discussion on the applications of stack. That is the first application we discussed that, recursion we discussed that. Fine. So now in this particular CDT, we are going to discuss about the second important application of the stack, which is nothing but generation of a Fibonacci series by using recursion. Fine. So the summary of the previous CDT is that we defined that recursion is nothing but calling the same function repetitively until some base condition is satisfied. And the recursion will have both base case as well as a recursive case. So base case in which the problem is expressed in a simple manner such that it can be easily solved without making any further call statements to the same function. Whereas the recursive case is nothing but the problem is first divided into smaller subproblems. Second, the function calls itself with the subparts of the problem obtained in the first step. And third, the result is obtained by combining the solutions of simpler subproblems. Therefore, recursion is nothing but defining the large and complex problem in terms of smaller and more easily solvable problems. And we had a discussion that recursion is an implicit application of stack ADT. So that is a system stack is used whenever we write any recursive function. So while executing of that recursive function, so the system stack will be used implicitly. So now in this current CDT, we are going to discuss another second important application of the stack, that is a Fibonacci series generation. So the objective of this session is that it will develop the knowledge in students based on this topic applications of stack using for Fibonacci series. The lecture outcome is that after completion of this session, students will able to develop the code using recursion for solving the given problem. Now coming to this, what is a Fibonacci series? So Fibonacci series in this, what we are doing here is that the next number is the sum of the previous two numbers. So initially we will take two terms. This is 0 and 1 we will take, and we will add these two terms to get this current term. So 0 plus 1, 1. Again to generate this current term 2, so we will add this previous two terms 1 plus 1, 2. To generate this 3, the previous two terms for 3 are 1 and 2. So 1 plus 2, this is 3. So like this, the Fibonacci series, this is nothing but the summation of previous two terms gives the current term. So the first two terms of the Fibonacci series are assumed it as 0 and 1, and we will go on generate the series. So there are two ways to write this Fibonacci series program or implementation of this Fibonacci series. Through the C program we can do. Without recursion, we can also write the solution for Fibonacci series, and using recursion also we can write the, or we can develop the solution for Fibonacci series. Fine. So mathematically, when we are going for a recursion function, so we can define the function in terms of the same function itself. So the Fibonacci nth term f of n is equal to previous two terms summation, that is f of n minus 1 plus f of n minus 2. So nth term in the Fibonacci series is equal to the summation of the previous two terms, that is n minus 1 the term and n minus second term. Fine. So the base values are f of 0 is equal to 0 and f of 1 is equal to 1. These are the base values, and this is the recursive case. Got the point? So to compute the nth Fibonacci number, this is what mathematically we can define the recursive definition. So for example, if you are calling this recursive function, this is a call stack trace, we can call it as recursive call track stack trace, we can call it as. So if you are calling that particular function with 5, then how that recursive call will be calling by itself that particular function. So fib of 5 is computed by fib of 4 plus fib of 3. Fib of 4 is nothing but it is computed as fib of 3 plus fib of 2, summation of previous two terms. If you add these two terms, fib of 3 and fib of 2, you will get fib of 4 value. So if you add fib of 4 plus fib of 3, you will get it as fib of 5 value. So like this summation of these two terms, we will get this fib of nth term. So like this. Got the point? So I hope this is what the call stack trace we are going to get whenever if you are calling this fib of 5. So all these calls take, because fib of 1 is already we will know that its value is 1, fib of 0 is, we know that 0, fine. So this fib of 5 is breaking down into fib of 4 plus fib of 3. So left fib of 4 is breaking down into fib of 3 plus fib of 2, and right fib of 3 is breaking down into fib of 2 plus fib of 1. So this process keeps on going till we reach the base condition, that is either fib of 1 whose value is 1 or fib of 0 whose value is 0. So in both the directions here we are going to compute fib of 1 and as well as fib of 0. Okay, so once we know this base condition is reached, so we are finally computing the value of fib of 4. So we are backtracking this fib of 1 plus fib of 4, that is fib of 2 value, we got it as what? 1. So 1 plus 1, fib of 2 is known, fib of 1 is known, so we got the value of fib of 3 is 2. So here 1 plus 1 is 0. So we got the value of fib of 2 is 1 we got here. So once we got 1 here, 2 plus 1, we got this 3 as a fib of 4. Similarly, here also in the back, so left is right subtree also, if you see that. So this is, we are going to get it as fib of 2 is 1. Okay, fib of 1 is again, we know that it is 1. So 1 plus 1, which is equal to 2. This is a fib of 3 value is 2. Then fib of 5 is nothing but 3 plus 2, 5. So if you write the series, this is 0th term, this is the first term, and this is the second term, this is the third term, and this is the fourth term, and this is the fifth term. So the fifth term in the Fibonacci series is 5. Fine. So this is how the call stack trace will be there. So all these calls will be stored in the system stack. So this is a programming part. So we have written that a recursive function Fibonacci of int n, we are passing the nth Fibonacci number we want to calculate. So if n is equal to 0, we have to return 0. Else if n is equal to 1, we have to return 1. Else we have to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this is what we are recursively calling this function. Okay, two times we are calling that. So that is the reason one left subtree as well as right subtree both call stack trace we have seen in the previous example. Fine. And this is the main function int n equal to 5. So we are printing all the 5 Fibonacci series up to 5 terms we are printing for I equal to 0, I less than n, I plus plus. So within this loop we are calling the Fibonacci of I. So I equal to 0 means we are calling this Fibonacci with the n value as 0. Okay, 0th term it will return that. If you call with I equal to 1, so first term I equal to 2, second term I equal to 3, third term I equal to 4, fourth term like that. So I equal to 5, fifth term like that we are going to get. We are calling the same function repetitively. To print the series, Fibonacci series, we are printing that. So if you see the time complexity to take this particular Fibonacci series recursive function, if you take that, so to find a Fibonacci series element using the recursive function approach, it is approximately going to take a big O of 2 power n it is going to take. The reason is as with each call, the function is breaking into two child calls. Fib of 4, we are calling it as fib of 3 plus fib of 2. Fib of 5, we are calling it as fib of 4 plus fib of 3. So the two child calls we are going here. Then again into two more child calls for each specific child. So again two calls. Hence the time complexity having using recursive approach is big O of 2 power n. So as it is growing with respect to the power of 2, it is going that. Okay. And coming to the space complexity, using the recursive approach will be big O of n, because as in recursion, the space required is proportional to the maximum depth of the recursion tree. So as the maximum depth is n, So the space complexity is a big O of n. Got the point? Because the depth of this tree, if you see that in this particular recursive call, the depth of the tree, if you see that it is approximately, we are going to get it as a 5. So 1, 2, 3, 4. Okay, so this is what maximum depth is 5. Okay, got the point. So that is what we are going to take it as the space requirement is big O of n. Now coming to the reflections part, what is the output of the following code? Anyone can guess. This is a recursive function we are given. F1 is a recursive function we are given. So if this x value is 1, return 1. This is what the base condition. Else x into f1 of x minus 1 we are calling that. Anyone can answer this question. Fine. So 4. So 4 into, it will call it as 3. Okay. Again it is not equal to, so 3 into, again it will call with 2. So 2 it is not here. So 2 into, it is going to call it as 1. When x equal to 1, we are going to return 1. So it will compute 4 into 3 into 2 into 1. So which is equal to, fine. 4 3 is a 12, 24. So the answer is 24, right? So if you are not able to answer this question, so please watch the video from the beginning. Okay, so the lecture outcomes are revisited here. After completion of this session, students should be able to develop the code using recursion for solving the given problem. So the summary of this today's session is that, so in this particular CDT, we discussed about the another important application of recursion, which is nothing but printing of the Fibonacci series. The recursive definition of nth Fibonacci number we have given as fib of n is equal to fib of n minus 1 plus fib of n minus 2 if n value is greater than or equal to 2. Otherwise, fib of 0 equal to 0 if n equal to 0, fib of 1 is equal to 1 if n is equal to 1. So recursion, which is an implicit application of the stack ADT, we have seen that, and the space complexity of this recursive call for printing of this Fibonacci series is big O of n, and the time complexity for finding of this Fibonacci series is big O of 2 power n. So which is the highest time complexity this particular Fibonacci series is going to take, 2 power n. So this is a lecture level practice problem. Write a program to a recursive function to find the nth Fibonacci number. Fine. So these are further readings on this particular topic. So if you have any doubts, you can raise the doubts in the classroom after watching this video. Fine. So thank you one and all.